Greetings, students of calculus. It has been a long time since the last time we met, and we are certainly under a kind of new operational procedure here with everything that's been happening in the world. Um, the purpose of this video is to kind of finish up the last few topics in calculus that I have not had a chance to teach you in class. So what I'm going to do is kind of run through the slides we would have gone through in class and teach you um, how to do volume using known cross sections, which is what we started about a week and a half ago, and then also teach you how to do volume using what's known as the disk method, which is essentially cross sections but with circles, and then teach you volume using what's known as the washer method, which is a little more complex, but essentially is the combination of two different disks being used for volume. We'll get to that though at the end. What I want to do right now is I'm going to start off with reviewing volume by using known cross sections. This was something that we did last week, and essentially if you're looking at the formula on the screen here, to find the volume using a known cross section, the key is that you take whatever the shape is that you're dealing with. If you know what the cross sectional shape is and you can find its area, then you can find the volume of the entire shape by integrating the area of that shape from wherever the region starts to wherever the region ends. So I'm just going to run through a couple of quick examples here. These are basically greatest hits of cross sections. The two most popular cross sections that you're always going to deal with are probably going to be squares and semicircles. Obviously it can be other shapes as well, but I'll run you through the two big ones for now. So we're going to look at this particular example here, where we're going to consider the shaded region in the graph that's bound by the function f of x equals the natural log of x. That's the top curve kind of moving along here. And then by the line x equals 10, so that would be the vertical line over here on the right side, and then the x-axis, which would kind of form the base of this particular region. Now they tell us that this region forms the base of a solid with square cross sections that are perpendicular to the x-axis, and our goal is going to be to find the volume of the solid. So what I want you to kind of picture here is that this green region is the bottom of the solid. So if you were to pick up this shape and look at it, that's the shape you would see on the bottom. All right. Now, if you have square cross sections that are perpendicular to the x-axis, that means we're going to have these squares that are coming out of this graph towards us, three-dimensionally, if you will. All right, and kind of forming this particular shape here, and then you just have to kind of imagine connecting all the edges here, you know, with lines and kind of forming the shape here that you would end up getting, and obviously filling in with a lot more square cross sections. But the general shape we're looking at here is a square, and it is perpendicular to the x-axis. X-axis is going horizontally, and the square is going vertically. So all of these squares here are going to be perpendicular to the x-axis. Now, to get the volume, obviously we're going to be integrating the area of one of these cross sections. And since the cross section is a square, all we have to do is find the area of one of these squares. So to pull this off, the first thing we want to do is draw the square two-dimensionally. So just taking one of these squares and looking at it two-dimensionally, our goal is to find the volume or the area of one of these squares. All right. Now, in order to make this happen, the key thing that we're going to want to do is determine what the length of the side of the square is. All right. So I guess the visual I'm going to have kind of draw to you here is if I kind of trace the bottom of the square here, I want you to kind of think of the bottom of the square as being this line segment right here for this square. All right, and we want to be able to determine what's the length of that line segment. All right, to get the length of that segment, what you're essentially doing here is you're getting the distance from the x-axis up to the curve. And since the curve is just defined as the natural log of x, that would imply that this length here is just going to be the natural log of x, which means the length of the square is also going to be the natural log of x. I'm going to apologize in advance. I am writing with a mouse here and I am not a pro. Alright, so we got this length of the segment is the natural log of x, and that would mean since the shape is a square, all four sides are obviously going to be equal. So the area of the square is just going to be found by taking the natural log of x and essentially squaring it. So what you're going to see next here is the area function for the square is just going to be the natural log of x squared. All right, and once you have your area function, all we're going to do now is we're going to integrate that to get the volume. And Since this region starts when x is equal to 1, that's kind of where this region is going to begin, and it's going to end down here when x is equal to 10, we're going to integrate from 1 up until 10 and use that to kind of help us get the volume. And when you do this, whether you use a calculator, you'd have to probably for a situation like this, you're going to end up with a volume of 24.967. Okay, so again, kind of recapping here, you get your cross-sectional shape. All right, you find its area. Since the length of the side is going to be defined as the natural log of x, because that's the distance from the x-axis all the way up to the curve here. All right, that's how far we're going. We can get the area as the natural log of x, the quantity squared, since we're dealing with a square, and we would then integrate that function and get 24.967. Okay. Now we're going to take the same region in the next example here, and we're going to now use semicircular cross sections. All right. Now semicircular cross section is a little bit harder. This is one of those scenarios where I would urge you to keep your work really organized. But first of all, to give you a visual, semicircles are going to kind of come out like this. All right, so this might look more like a loaf of bread to you or something to that effect. Okay, but semicircles you would imagine are coming out of the graph towards you here, and we want to recall that we're still going to be integrating the area of one of these cross sections. Now, the cross section that we're dealing with obviously is not the square anymore, it is now a semicircle. All right, so we got to be really careful here, because the length, or in this case, diameter of the semicircle is going to be this red line here. Okay, and just as it was the case with the square, the distance of this diameter is going to be defined by the height of the graph here from the x-axis up to the curve. And so that means that our diameter here is going to equal the natural log of x. Okay, now you will hopefully recall that if you want to get the area of a semicircle, you're going to need to do the area of a circle, which would be pi r squared, and you would have to find the radius. All right, now since the diameter of the circle is the natural log of x, the radius of the circle is going to be half of that. That's really, really important. Now, if you're using a calculator, I would strongly urge you to define r of x on your calculator as 1/2 times the natural log of x. Just do it right on the calculator screen. Define it as 1/2 times the natural log of x. All right. Now, once you've gotten that, the next step is to build the area function. To get the area of a semicircle, you're going to need to do 1/2 times pi times the radius function squared. Now, we define the radius function down here, so we're going to want to put that up here into the radius function. But if you're using your calculator and you defined r of x already, you don't need to redo that. You can just actually, what I would urge you to do on your calculator is now define a of x on the calculator and just call it 1/2 times pi times r of x, the quantity squared. And when you do that, you're now set up to now go get the volume. And in this case, we're going to do the volume is the integral from, again, 1 to 10, because the region's starting at 1 and it's ending down here at 10. All right, and you're going to integrate this area function that you've already defined in the calculator, and when you do that, you will end up with 9.805. All right, so that's just kind of a quick synopsis of finding area or finding volume using known cross sections. Again, for the semicircular region, I would strongly urge you to use your calculator and first define what the radius function is, and then define the area function using the radius function. And then that's going to make your integral computation much, much easier on the calculator, because you don't have to write all that stuff out. You can just kind of literally define r of x, define a of x, and then do the integral from 1 to 10 for a of x dx, and you'll get your answer. Okay. Now, the next topic, and this is where we're going to venture into new territory here, is we're going to